What's that on me now? That's a lot of people in one lab. Like, that's like my semester second class.
Hey, then we can go to the afterlife together. What killed job chemistry?
I do good. I'm hating that I have no energy right now. I can't even leave a class because the rich
What I'm worried about is
I'm like chill around for a little bit. I need cash.
Oh yeah. And it's like
kind of practice problems and stuff.
it's really
Right.
I'm taking
All right, make sure I got everything set. Organic Chemistry 2, MOTS, more of the same. So, anyone not have me last spring? Decent amount of people. So, what I can say about that is you will want to go into the textbook, which is online. Definitely look at NMR and IR and mass spec. We'll be doing a lot of that this semester. So we use those as tools to figure out like what product was made. That's probably the most important stuff you'll need from that semester. So we meet Monday, Wednesdays in this classroom from 1 to 2:15. You're paying a lot of money to be here, so I will go until 2:15. So please don't start packing up at 2 or 2:07 or something like that. We have a lot of material to get through. My plan is to cover it at a reasonable pace, but not so fast that you don't understand it. There's plenty of time for questions, so please ask questions. I'll explain what that sheet is, but if you want to go ahead and put your name in the name box, your USM ID in the number box, fill in the bubbles.
Can we use a pen on this?
What?
Can we use a pen on this?
Yes. So that sheet is for the not attending roster, which is required by the university for the first day. We won't do too much of the zip grade in class. I'll explain the points and all that stuff as we go through. Please read the syllabus. I'm not going to spend this lecture talking about the syllabus. I'll sprinkle things in the lectures as needed in terms of earning points, grading, and all of that stuff. One other thing, as I told my Organic 1 class this morning, I care about humanity. I care about everyone in here and hope everyone does well, but please do not email me if you miss lecture. It's not necessary. Actually, there's a university policy that it's a minimum of 3 lectures before an official notification has to be made by you, the student. And that's relevant as well, as I'll explain as we move in terms of the grading. So we'll jump right into it here. My name is Matt Donahue. These slides are, something happened between spring and fall and the summer. They changed this app, so the slides look really small. My office is Tech 429. My lab is 406. My formal office hours are Monday, Wednesday from 2:30 to 3:30. If you can't meet then, just send me a email and I'll respond with a calendar invite that we can meet. Any course communication, please do that through Canvas so that all that stuff's tracked. I'll try to respond within one business day. If not, send me a follow-up email because things get stacked and I lose track of stuff. Okay, so as I said, we're gonna get right into it. There's, I think, 6 modules. I reconfigured some stuff for the fall based on my spring cohort. So we're gonna start with conjugation and lipids. And the reason for that is we finished the spring semester looking at electrophilic addition to alkenes. And so conjugation is directly related to alkenes. And now we have more double bonds. And the word conjugation has a specific stability property that will translate into the next module, which is called aromaticity. And then from there, the layout of the course is looking at the oxidation state of carbon in terms of classifying functional groups. So we'll do conjugation, then aromaticity, and then we'll get into the individual alcohols, aldehydes, acids, all that sort of stuff. And then the last module is on biomolecules, so carbohydrates, amino acids, peptides, proteins. And then that's your sort of handshake into biochemistry if you go into those courses. So again, we're only going to do this form officially today once, and then this is for a bonus of, I think, 2 points or something, but this is the NA roster for the provost. So please fill out your name, your USMID with the bubbles, and then the question is, what is the general molecular formula for an alkene? What functional groups do alkenes have? So a carbon-carbon double bond. So remember we used, when we were determining degrees of unsaturation, we had to use the formula for an alkane to figure out how many rings or pi bonds were there. So if you remember what the alkane is, you should be able to figure out what the alkene is. Everyone good? It's only one question, so it's not much more involved than that. Anyone need more time? So upon leaving my Organic 1 class, I had a bit of a snafu with these sheets. I grade them on my phone, and the phone was not recognizing them for some reason. So I'm in for some pain tonight manually doing this. If it works, you'll see a photo of your sheet in your ZipRate account. So your student ID is your USM ID, no W, no leading zeros or anything like that. Student access code is the ZipRate code. How many people have found theirs already? Just 2. Where did you find it? So if you go to your assignments, it says like accessing ZipRate or something, there's a comment in there. And then the comment has your unique code. So don't share that with anyone, because then they'll be able to see your account. And that would be bad. So if it works, you'll be able to see the picture of that after I grade it. If you don't see anything in there, then things are horribly wrong. But you're going to take your module exams through ZipRate. So I think you have 7 or 8 module exams. You'll log into ZipRate to take those. So you'll see the questions, and then you have a response thing over here. You click the bubble. 30 questions, submit it. And then, so when the module ends, you get 24 hours to do that. There's no time limit. Like once you start, it's not timed for like 75 minutes or anything. You have the full 24 hours. Question? So those exams you'll take outside of class. And the days and times that they're open is listed in the syllabus. And as I said, I care about humanity with an asterisk to that. If your arm has fallen off or something, I still expect you to take the exam during that 24-hour window. This software does not allow me to give individualized dates. So please look at the syllabus, mark those dates and times in your calendars so that you know when they are. Even if you're traveling, there's Wi-Fi across the globe, so you can still log in and take the exams. If you don't take the exams, those 60 points are moved into the final. So this is all explained in the syllabus. So you are penalized for that because the value per point lowers. So make sure you understand that policy. It's in your best interest to just take it and get as many points as you can, because if it moves into the final, you're going to get the short end of the stick there. So once a module ends, that's when the exam opens, like that day. So 2:15, the module, we get done lecturing. That exam opens, you have until 2:15 the next day to complete it. So you do those outside of class, online, make sure your internet and all that works. I'm not iTech, I'm not Bill Gates, I can't help you with computers and stuff, so those kind of emails to me are gonna fall flat in terms of any help I can offer. The only exam that you have to sit in this room for is the final exam. So that's required, and so I made the study guide a required part of the course now. So your textbook and then this other workbook are all located in Canvas through the course resources. So however you feel about looking at ebooks, that's another thing, but this you have to go buy. And so this study guide, again, it's broken up between semesters 1 and 2. so it's a little bit easier to find stuff, but this will help you to prepare for the final and so that you don't feel ambushed about the difficulty of the final exam. So if you go into Canvas and look at your grades, you should see sort of the required points already sort of shown in there as assignments. The thing you're doing today is a bonus, and so there'll be little bonuses throughout the semester to pep up your required points. That said, there's no redos or makeups or early or lates, so most of the stuff's going to be in class, so you're either here or you're not. I don't want to get into keeping track of absences and stuff. And maybe today or tomorrow, I'll also post an Excel file where you can start keeping track of your points. So if you get these 2 points, you just go in the Excel file, you hit 2, and then it'll start calculating your grade in real time. But keep in mind, it's for the points available until now. It's not like for the entire semester. So as you put numbers in these cells, you can sort of see where you're going. And then that's going to give you an indication of how you need to perform on the final. Any questions? So maybe let me just kind of warm us up here, what we left off on, so that we understand what we're going to do in conjugation here. So I'm going to scribble this stuff in this app called Explain Everything. Then I'm going to make a video of it, upload it into YouTube, a 256 fall playlist. So if you're not here, or if you are here and you want to review stuff, you can see these screencasts later on. So the alkene functional group has a carbon-carbon pi bond. And so those are the elements that are sort of embedded in that term alkene. So what was the molecular formula for alkenes? CnH2n. So that's the general molecular formula. So remember that a pi bond is a degree of unsaturation. That just means it has lost an equivalent of H2. Because it's an alkene, we know it's a pi bond. A degree of unsaturation can also be a ring. Those also have a formula of CnH2n. So here's a molecule with 4 carbons. And we have an alkene starting at the 1 position. So this would be called 1-butene. So one of the things we left off on in the spring semester was additions to those pi bonds. And this was electrophilic addition. In terms of describing the mechanism, the pi bond is a nucleophile. So a nucleophile supplies electrons. And say we wanted to do a hydration reaction. I'll just write H3O plus. So we're going to add two elements across that pi bond, an H and then an oxygen. So this was hydration. So that means we added formally H2O. So if the pi bond's the nucleophile, the other reagent has to be the electrophile. And so this happens in a regiospecific manner. So that term means that between carbons 1 and 2, by the way the mechanism occurs, only one of them can get H and only one of them can get oxygen. Does anyone remember why that is in terms of how this mechanism proceeds?
Is it because carbon 2 borders two other carbons and carbon 1 borders one?
It's getting there. There's a specific type of intermediate that's formed, and you have to evaluate the stability of those intermediates. So with the pi bond in the hydronium ion, there's an acid-base reaction that happens to form a carbocation. So carbon 1 gets protonated, and in doing so, it generates a carbocation at position 2. So that's a secondary carbocation, which is more stable if we flipped it around and protonated carbon 2 versus 1. So the water then attacks that. Got a little crazy here. So we generate this intermediate, which then reacts with water again to do an acid-base reaction. And so now we end up with a new molecule, an alcohol, and this is called 2-butanol. So as we go through the reaction conditions, the mechanisms, we'll talk about nomenclature, we'll talk about spectroscopy, so IR, NMR, mass spec. And the goal really is to touch upon everything that you'll see in the final exam, things that you want to be aware of. So that's one of the set of conditions for electrophilic addition. And with conjugation, what we're going to do now is look at molecules that have more than one double bond. And then of that, a specific subset of those structures that undergo some reactions. Questions? Next. So as a review, degrees of unsaturation, or DOU. A degree of unsaturation can be a pi bond or a ring. So now think of the different types of pi bonds that we know. So carbon-carbon, carbon-oxygen, or carbon-nitrogen. And then a ring can be any size 3 or greater. So a degree of unsaturation is telling us a little bit about what functional groups can be present in a molecule, in a molecular formula. So experimentally, that's measured through an addition reaction. So we have hydrogen gas. That's coming down to the alkene. The mechanism's a little bit more complicated than what I'm going to draw, but in terms of pushing the arrows, we can say the pi bond will abstract a hydrogen. This bond then comes down to form another CH bond. And then overall, we've added H2 to the molecule. And so you can rearrange this piv nert here for N. Experimentally to determine the amount of hydrogen that was taken up in the molecule. So visually, when you see a structure and look at it, you're just counting the pi bonds and the rings. That gives you degree of unsaturation. But experimentally, if you had some unknown substance and you had no idea what it was and you wanted to figure that out, you would hydrogenate it, look at the pressure valve on the hydrogen tank, see how much it dropped, throw it into this equation, and you'd calculate N, and that would give you some idea of the degrees of unsaturation. So we're going to continue on this discussion of electrophilic addition and talk about those terms regio and stereoselective under the context of conjugated systems. So say we have this alkene, which I've labeled carbons 1 and 2. And then we have that electrophile A and B. So regiochemistry means which carbon's getting A and which one's getting B. So that's one possible product, or if we flip it around, that would be another one. And so what we need to think about if one starting material can produce two products, what's the relationship of those products? And then what analytical techniques can we use to differentiate them? So that gets into the IR, the proton NMR, carbon NMR, because they'll have the same molecular formula. Mass spec really isn't going to help us here. Questions? So what does conjugation mean? So in general, we're talking about polyunsaturated molecules. So poly means many. And then unsaturated in this context is going to be our pi bonds. Within polyunsaturated molecules, there's 3 subtypes, and conjugated is one of them. So, for example, we're talking about molecules with 2 or more double bonds. These different types are the relation of those double bonds to each other. So there's cumulated, conjugated, and isolated. And we'll show examples of those on the next couple slides. Cumulated means a 1-2 relationship. So wherever you see a pi bond, you start counting. So you see a pi bond at carbon 1, it goes to carbon 2, then immediately at carbon 2, you see another pi bond. That's cumulated. Conjugated means 1-3 relationship. So there's a sigma bond that separates the pi bonds. And then isolated is a 1-4 or greater relationship, meaning that you have an sp3 hybridized, probably should say atom, but it says carbon. You have some other atom between those pi bonds. And the one that we're going to focus specifically on are the conjugated. So I'll show you examples of what cumulated is. You kind of already know one. So if you take a deep breath in and then exhale, what are you exhaling? Carbon dioxide. So that's a cumulated molecule. Conjugated is special. We'll talk about why that is. Isolated is just the stuff that you learned at the end of 255. Those double bonds react just like alkenes. It's the conjugated ones that we have to think a little bit more about. So here's some examples of each of those. The first set here, these are called acyclic. This app. So acyclic means without a ring. And so these molecules are dienes. So di means 2. Ene means alkenes, so there's 2 pi bonds. So the first one shown in red, that's cumulated. So if we number the carbon chain, so 1, 2, 3. So at carbon 1, there's a pi bond. We get to carbon 2, we see another one. So that's the definition of cumulated. They're like right. Well, let me say it this way. They're sharing 1 carbon of those double bonds. So they're sharing that central carbon. So this is the special one here, the second one, conjugated. So this is the sort of pattern you're looking for. So let me number these, 1, 2, 3, so 4 carbons. As we trace the backbone at carbon 1, we see the alkene, and then what's separating them is a sigma bond, just one sigma bond. And then carbon 3 is starting the next alkene. So we have pi, sigma, pi. And the last case, these are called isolated, that's in green here. So the molecule is a diene. The pi bonds start at carbon 1 and carbon 4. So carbon 3 is what hybridization? So sp3. So it's isolated because you have that carbon that's at a different hybridization state between the two alkenes. And again, the alkenes in this molecule just behave like the reactions we learned last spring. Accumulated ones are kind of beyond the scope of this class in terms of their reactivity, but the conjugated ones are what we're going to focus on. How do the two alkenes, when they're separated by the sigma bond, affect the reactivity? The next set of examples, these are cyclic. So they have a ring. So a ring and then di, alkene, so two of them. Notice there's none of these cumulated examples that are cyclic. And so the reason for that is the ring size would have to be pretty big to accommodate the hybridization required. So the three in blue here, this 4-membered, 5-membered, 6-membered ring, those are all conjugated. So you see the diene, there's a sigma bond, there's a sigma bond. So pi, pi, sigma, sigma. So the next one, don't confuse yourself when you're looking at it and think that it's isolated because it has this carbon here. So if you're looking at it kind of going counterclockwise, so like here, you have pi, sigma, pi. So that falls under the conjugated class. If you went around this way, it was like, okay, there's a pi bond, but that's sp3. You'd say, well, that could be isolated. It's not. So you're looking at something that minimally matches the definition. The 6-membered ring, this is also conjugated here. But notice it's tethered together by sp3 hybridized carbons. So let me find the... So that's the conjugated part. So stated another way, in terms of the reactions that we're going to look at, like for this 6-membered ring, these two other carbons, like nothing's going to happen there. So the action is only happening at this diene part of it. So the last example is the isolated one. And so we've identified the alkenes, but notice they're separated on each side by an sp3 hybridized carbon. Questions? So this, as I said, it's more of the same. These are now trienes. So tri means 3. So you can have these cumulated trienes. So this is buta 1, 2, 3, 4. So buta 1, 2, 3 triene. Anyone like astronomy, physics? So these type of molecules have been identified in space, which is interesting because nature will pack these molecules with a lot of unsaturation, meaning that when they finally land on Alpha Centauri somewhere, something can react with it, and from that reaction, billions of years later, life will evolve or be created, however you view it. So again, you can pack these things on if you want to fill your paper with 10 of these. You could draw a accumulated system with 10 alkenes bonded to one another. So here's a triene. So we have 1, 2, 3, 4, 5, 6. That's where this hexa comes from. The 1, 3, the 5 tell you the start of the double bonds. And the triene is just confirming that there's 3 and what functional group they are. Anyone remember what that designation E means? Huh? That's a different E. When you have E or Z for alkenes, it's telling you the geometry of the alkene. So cis or trans are also used for that purpose. So E means apart, and just let me review on how we get E. So there's the carbon chain. So I'm going to put in the hydrogens. So H and H. So let me switch it up here. Call that blue. Call this green. So the blue and green dots are your sp2 hybridized carbons. And then you have to assign a priority to each substituent on them. So you have an H and then a carbon. So you have H and then carbon. So you use the atomic number to assign a priority. Carbon's a higher atomic number, so that gets priority 1. H gets priority 2. So let's do it in black here. So priority 1, priority 2. And then you do the same thing for the green dot. 2 and 1. And then you look at the relationship of the priority 1 functional groups. They're on opposite sides of that alkene, so this is E, or trans. Our last example here is the isolated So we have 8 carbons, double bonds starting at 1, 4, and 7. So carbons 3 and 6 are sp3 hybridized, so they interrupt the flow. And so I have this molecule here highlighted in blue, so that should be a red flag or a light blue flag. You have a question?
What did you say one more time after you placed the priorities for the second molecule? How did you figure out that it was E?
So here's your pi bond. Of the substituents, you're locating the highest priority. So on this side, there's the 1. Over here, the 1's on the opposite side. So that would be trans. That's a little bit easier to remember than E or Z. So I have this highlighted in blue. It says cyclic trienes. So in theory, we could name this molecule. There's 6 carbons, 1 ring, and 3 pi bonds. We could say cyclohexa 1,3,5 triene. Does anyone know a more common name for this molecule? It's benzene. So there's a subtle distinction about conjugation and then this molecule, which is called benzene. It's easy to spot that the triene is all conjugated, right? Because you have pi, sigma, pi, and it alternates like that. So it meets the conjugated part. But the fact that the termini of the chain are connected together in a ring, that ring adds another stabilization factor called aromaticity. So what I decided to do this year was break out conjugation into one module and then aromaticity into another. So they're separate modules, separate exams, because there's a lot of stuff to digest for them. So we're going to talk about benzene all by itself due to that word called aromaticity. Any home chefs in the crowd? What does aromatic mean?
It has a smell.
It has a smell. So that's typically what the original meaning of aromaticity meant. Like benzene has a smell. It's a little off-putting. You probably don't want to be huffing it all day long. It's not totally unpleasant. It's not like roses are pleasant or anything, but aromatic compounds do have that smell. But for this class, that word aromaticity means something special that's measured experimentally, not just smell. So that's module 2. So a brief aside, I said we weren't going to talk too much about cumulated systems, but there's an interesting feature that arises from them. So as we see in this propane derivative, so there's 3 carbons, so it's a propane derivative. The double bonds start at positions 1 and 2. The little dot there, so this dot, that means carbon. And so alongside the right, I've shown you the hybridizations. And what's interesting about these is because the double bonds are sharing that carbon, that has to be sp hybridized. So you remember the p orbitals? They lie on different axes, right? So the pi bonds of this first alkene between 1 and 2 are going to lie in one plane. Then the pi bonds between 2 and 3 lie in a plane that's 90 degrees from that first alkene. And that's demonstrated subtly if you're not aware. See these CH bonds here, how they're just normal bonds? That means they're in the plane of this projection. Notice here at carbon 3. See how that's a wedge and that's a dash? The wedge and dash indicate stereochemistry. So that bold wedge is projected out towards you. The dash is going into the classroom back there. So as you walk along this molecule, the carbon-carbon backbone, if you started in this plane on that H and you walked along to that, you would be in a different plane due to the orbitals being 90 degrees from one another. Anyone know what a Moebius strip is? Moebius strip? Mobius?
Yeah, it's
What is it?
it's made with one side.
It's a 3D surface with one side. So these, you could kind of convince yourself it's something like that. You take a strip of paper, you like twist it and then staple it together. If you put your finger on it, your finger will never leave that side, but you'll trace both sides of it. So probably more towards the end of this semester, we'll start talking about other 3D shapes, specifically like with DNA. So what's the shape of DNA? It's a double helix. And so that's interesting because helices can also have chirality. So any do-it-yourselfers, carpenters in the crowd? If we go to Home Depot and you buy some like normal screws, what direction do you have to turn your hand to make a normal screw go into wood?
Right.
So clockwise. Does that then preclude that if you go the other way, like you couldn't have any screws that do that? You can get left-handed screws that will still drive into wood. They're just less common. So that's another question. Why is that? How many of you are left-handed? So what, 4? How many of you are right-handed? So that's why a normal screw does that, because most people are right-handed.
And underhand.
You can still get reverse threaded screws like on your bike pedals, if you notice. If you try to put it in the normal way, you're going to strip the thread. So trust me, I've done it. So we'll talk about like symmetry and chirality in other forms that we haven't seen so far, like with the R and S stuff, how that translates. So if you put your eyeball right here and look down the axis, that's how those hydrogens appear to one another. I'll give you the 30-second crash course here in this. This won't be on the exam or anything, but it is kind of interesting. the laser here. These two molecules are enantiomers. But a lot of the enantiomers that you saw in organic 1 were from sp3 hybridized carbons, right? They had 4 different substituents. You could assign priority. It could be R or S. But notice in that axis here, there's no sp3 hybridized carbon. However, because the orbitals twist into different planes, you can get these enantiomers. So you cannot overlap these and have all the substituents match, so they're enantiomers. And so you can still assign R and S to them. It's just done in a little bit more convoluted way. And ultimately, you can assign R and S to DNA. But think about that, because you're assigning R and S to the twist of the molecule. So you take physics yet, anyone? Like the curl rule? Like these are enantiomeric helices right here. So I don't tell you this to scare you, but just to sort of introduce it, that even things that you've been exposed to, you might not have thought about these things. And towards the end of this semester, when we end up at biomolecules, which are you and me, we're just a large collection of different things, like you can start asking these questions, why? So DNA spirals a certain way for everyone, unless unless something has gone terribly wrong with your genetics, it will spiral the other way, which it probably hasn't. But then think of why that is, like what led to that. And it's a lot of this fundamental stuff that we're covering now. Any questions? So, like I said, we're going to go until the time's up. And so what we'll get into now are some reactions of these conjugated systems. I mean, what you'll find is it's going to do the stuff that electrophilic addition does, but the presence of that other alkene gives it a little twist that we have to consider. So these were just some examples of the cumulated things. We talked about carbon dioxide. You can swap out carbon for other elements. The other reagent we'll see in the last module. Let me see where we're at here. To the reaction yet. Let me spend some time talking about conjugation. What does the word mean? What is it implying that makes a normal alkene sort of react differently when they're next to one another? And really, it's best explained by that heat of hydrogenation experiment. So when we were figuring out degrees of unsaturation by adding H2, that's a hydrogenation. You can set up a reaction, measure the pressure difference, but then also measure the heat output. So let's look at this first example here. So we can see one pi bond, it's going to add one equivalent of H2. And then it's also putting something else out. So heat, which is measured with a change in temperature. So in this table, we have different substitution patterns for alkenes, alkenes in polyunsaturated systems. If we take, so 1 butene, that's going to add 1 mole of hydrogen. The output that is measured is negative 127 kilojoules per mole. If we take 127, divide by 1, we're just normalizing it in this column. The second example, we've just added another carbon to the chain. This one's negative 126. That divided by 1 to normalize it, we get that. So you can see that for a monosubstituted alkene, they're all going to evolve about the same amount of heat. If we take that alkene and now put it inside the chain, still 1 double bond, 1 mole of hydrogen. Now the value is negative 115. So that divided by 1 is negative 115. I always have to recalibrate myself every time I teach this in dealing with negative numbers. So when you're thinking about this in terms of comparing, because the comparison of that number is going to translate into stability. Let's just think of 0. And so with negative, we want to just think going down. So when we're going down, we hit negative 115 first. Then we hit negative 127 or whatever. So negative 115 we hit first. That means that alkene is more stable, because negative 127 is evolving more heat. So let's look at an isolated diene. So they're separated by the sp2 or sp3 hybridized carbon. Now we need 2 equivalents of H2. The heat output is a total of negative 254. So that divided by 2 normalizes it to negative 127. So those alkenes just behave normally, like they're just normal alkenes. But what makes the word conjugated special? Now you have 2 alkenes, there's the sigma bond that separates them. So we need 2 equivalents of H2. This evolves negative 239. So that divided by 2 gets you this. So notice it's not the 127. There's a little bit less evolved. So even though it's small, that little bit of energy difference is due to the term conjugation. It stabilizes those alkenes. And structurally, what that relates to is resonance. So that's going to come back to haunt us. We need a firm understanding of resonance and why, when we put these alkenes next to each other, are they more stable than when they're isolated? And so that word conjugation affects the reactivity of the alkenes and how they do the additions. We're not quite. So I think I want to skip this slide because I kind of talked about most of it already. And let me get a drink before I start frothing here. So I will be the first to admit this is not easy to understand. So there's some shapes, some colors that are meant to indicate p orbitals. P orbitals. We're going to start with just an alkene on the left, and then on the right is a diene. And this will extend up to conjugated trienes, tetraenes, pentaenes. There's just a couple of things that we need to pay attention to. The color of the orbital will help us predict things. And ultimately, that relates back to resonance. So let's just look at the sp2 hybridized carbons. In these wedges and dashes coming off can just be sort of anything else in the molecule. We recognize that because there are two bonds, there's a sigma bond and a pi bond. What you're seeing in terms of these orbitals is the pi bond. This line connecting them, that's the sigma bond. We're not going to discuss that. Each carbon is supplying a p orbital. Do we all buy that? So each carbon supplies a p orbital. In that p orbital is one electron. They get together, so that's two electrons. That forms the pi bond. These things here, and again, I don't know this stuff, so you can believe me or not believe me. This picture is the output of a mathematical equation. It's called the Schrodinger equation. So it's just a visual. This is just a visualization of some equation that will fill the entire whiteboard. So p orbital and p orbital. Why are they different colors? It has to deal with the phase of that equation. So if you think of a sine wave, it goes up and then down. So if you think of like the up part, that can be your red, and then the down part is like the blue. It's just a qualitative representation of some math stuff. When the phases are matched, that's the bond. So phases or color So each carbon's supplying a p orbital, that makes a bond, and then I have something else above it. Why is that? So the reason is that you have p orbital, p orbital. That's two things. When they bond, they also have to output two things. The lower energy psi1 thing is a bonding orbital. This thing above it is called an anti-bonding orbital. And so notice the energy. Anti-bonding orbitals are always higher in energy. So one electron, we put them in there, they form that pi bond. So we've accounted for both electrons. So the anti-bonding orbitals have no electrons in them, but they exist because the mathematics in nature says they have to. That's what the star means. Anytime you see like that wave function in the star, that's an anti-bonding orbital. and then see this word node? What do you think's happening based on what you see? Say it again.
They're like meeting. They're like intersection.
What's happening to the colors? The colors are mismatched. So whenever those phases are not in alignment, that's a node. A node means there's no electron density in that region. The orbitals themselves are empty. And so you could ask the question, if they're empty, why are we talking about them? Well, we have to use them when we study mechanisms. When you're forming a bond, a nucleophile supplying electrons, right? Where are those electrons going? They can't go into a bond that's filled. It's already filled, it's taken up. They have to go into the anti-bonding orbital, which is empty. And so that's a little bit of the turn of the screw here in 256 is that deeper understanding of electron flow to rationally predict things. So let's look at this next case where we have alkene, sigma bond alkene. We have 2 alkenes, that means we have 4 p orbitals. And so how many of those wave functions do you see now? So if we count them 1, 2, 3, 4. So there's always some symmetry to this. So notice where the asterisks start at 3 and 4. So there's the symmetry. The regular stuff, these are your bonding orbitals. The stars that indicate anti-bonding. So psi 1 and 2 are bonding, 3 and 4 are anti-bonding. So for the lowest one, how many nodes are there? So there's 0. Then as we go up, how many are there? So psi 2 has how many nodes? So see how all these colors are aligned? So see how it flips? So that has 1 node. So the short answer of this is whatever that number is minus 1. So 0, 1, 2, and 3. So we flip, there's 1, those are overlapped, so there's 2. So 1, 2, 3.
Oh.
So that, again, you have a bonding orbital that has a node. It's just telling you that within that region, there's no electron density. So we didn't quite get to the reactions, but we'll pick that up on Wednesday. But the point I want to make about this is, how many of you eat carrots, cantaloupe, grapefruit? So what color is a carrot? Orange. What color is cantaloupe's also orange? I don't know, honeydew. So why did it have those colors? So the molecules in those fruits and vegetables, they have really extended conjugation. So the more of these double bonds you add into a molecule, the more it moves it into the region of the electromagnetic spectrum, the visible region, then you can see it. So we'll talk about how many of these do you need to start seeing a color in a molecule? And then why is color important to us in life? Any RFK Jr. fans in the crowd? It's taking away your food dyes and your Fruit Loops. So this can explain why that is. So if you could turn in that sheet, I'll try to get that graded and post your stuff on ZipGrade, and then we'll see you Wednesday. Okay.